Hello everyone, my name is Amir Al-Anizi and I'm a PhD student at KAUST. Welcome to my presentation. My presentation is about a fundamental and critical analysis that should be done to assess the capillary sealing efficiency of Carborex if we are going for hydrogen and carbon dioxide storage underground. To start with, let me talk about the motivation. So the plots in the slide showing you the watt consumption of energy throughout the years, and over the past years there was a growing demand on energy that mainly attribute to the accelerated growing numbers of population worldwide, which is here mostly compensated from the fossil fuel like oil, natural gas, and coal. The problem here is that all of these are contributing mostly to the greenhouse gases represented by the high emission of carbon dioxide in the atmosphere, and according to many reports, half of that huge amount of emission of carbon dioxide is only absorbed by the nature, and the other half is released in the atmosphere, causing the problem that we know as the global warming and the increase of temperature of the planet, and that will superimpose a lot of great problem to future generations. And that's why governments and countries have adopted strict environmental regulations to reduce the emission to the atmosphere by adopting, let's say, a low carbon diversified based economy, which includes the sequestration of the emitted carbon dioxide from high emission sectors, and be able to implement some decarbonization technologies that allow us to further reduce of our carbon emission. Now we know that these regulations thereafter sequestrating CO2. Now how about hydrogen? Where do we see hydrogen in the whole decarbonization process? Hydrogen, and according to many reports, that it's been regarded as a key player that will play a major role, as hydrogen has a unique characteristic of storing energy, a higher let's say energy density per unit mass compared to other fuel, and that could help to the decarbonization process by converting many of the fossil fuel into more environmentally friendly form of fuel, which is hydrogen. So there are many production processes that allow us to produce hydrogen. Those that come from, for example, the hydrocarbon and natural gas that goes through the steam reformation process that help to blend our produced hydrogen from the produced CO2 to become a mix between both, and allow us to have them underground without emitting any of those into the atmosphere, and again having a much more let's say clean fuel type, which is referred to into the industry as blue hydrogen. And on the other hand, we have also the green hydrogen, which is produced from renewable resources, and those could go through the process like the electrolysis process, which splitting the hydrogen from water through a sophisticated process, and that type can be also a hydrogen can play a major role into the overcoming some seasonal problem related to those renewable sources like wind turbines and solar energy, which could be cutting throughout the season, and by converting them to hydrogen, that will allow us to authorize that for the decarbonization of many of the high emission sectors. Now we need hydrogen, we need CO2, or we need to sequester CO2. This camera show you a diversified, and how is the diversified low carbon economy would look like. We will be able to blend the two initiatives of producing hydrogen and the sequestration of CO2 with other techniques like geothermal techniques. Now, the CO2 could be also utilized in enhanced oil recovery techniques, and options for storing hydrogen and gases in the surface in general is very limited, which could only offers like very limited capacity. Could goes up to megawatt of energy supplies if you're talking about the supplies that could last for days, maximum a few months. But comparing that to the underground options, we would have a much more larger scale of capacity to be stored if we go for underground storage. Options could include salt caverns, depleted gas reservoirs, and saline aquifers. Those are the most known options. Now, storing gas underground has been exploited several years ago, and the experience into that is very well known. CO2 sequestration, saline aquifer, for example, and trapping the CO2 through the mineralogy and solubility process are also very well known for now. But cyclic storage of hydrogen in the geological formation is still an area to be exploited, and that because hydrogen has the requirement of, so we need to inject hydrogen and be able to reproduce it back, and then to do that there's a requirement of having a cushion gas that could maintain or should maintain the hydrostatic pressure inside the reservoir not to collapse if we're going for cyclic injection production. The entrapment of gas could happen into two key techniques, one of which is the structural entrapment of the percolated free gas, that when we inject gas will displace the wetting phase. In this case, it could be the formation prime. Some of that gas will percolate and accumulate at the top of the reservoir, which is trapped by the impermeable layer called caprock. And that's one of the trapping mechanisms. The other type is the capillary residual entrapment, related to the wettability characteristic of the reservoir rock, trapping the gas into a very strong water wet rock. Now, in our presentation and our work, we'll focus more into assessing the integrity of the caprock and how efficient they can seal that free gas portion, and what will be the capacity that we can go for as maximum height of the gas column, and that lead me to our objectives. So we would like to investigate capillary sealing efficiency and capacity using wettability characteristics of the caprock. In this case, in our analysis, we're using pure mica being used as a proxy of caprocks for in so many publications, and thus we're using that in our study. Also to assess key parameters that could influence the efficiency of our caprock, related to the pore throat radius, temperature, and pressure, and then compare our pure mica analysis to the experimental investigation using slightly more realistic conditions of the geological situation of caprocks, and that by introducing or synthesizing a sample with an aged organic acid. Caprocks, they commonly include some organic acid that could range from carbon atoms of 2 up to 26, and that's what we're trying to mimic in the experimental side, and then we'll further repeat the analysis to compare the pure mica case with the high concentration organic acid mica. All of that under reservoir conditions and using a relevant prime salinity of 10% in ACL. Finally, organic acid could have a negative impact, and that's what we'll show in our slides. A method to mitigate that by restoring wettability. Nanoparticles is one option that has been exploited by the presented work, and we'll also assess how can nanoparticle be used and exploited at the lab. So this is basically our objective, and let me start with some definitions and concepts. So for example, the method that we're using is the tilted plate technique introduced by Lander in 1993, which basically based on a tilted face that is at a certain angle of 17 degree, and having a brine drop surrounded by the gas environment, and then we'll have the two contact angle tails. One represent the receding contact angle, which is related to structural entrapment, and then we have the advancing contact angle on the other side, which represent the capillary residual entrapment. The system's been, since its introduction, has been extensively used, and that's what we use in the whole analysis of the two cases, the hydrogen dynamic contact angle measurement, and also for the CO2. Now, this is about the equipment methodology. The analysis is basically using the fundamental capillary pressure equation that is a function of the interface tension of the gas and liquid, and also as a function of the effective pore throat radius inside the carborac. And at the same extent, we can also relate the maximum height exerted by the free gas against the capillary interpressure. The relation, or we can find that maximum height as a function of the density difference between the liquid and the gas, and that's what we attempt to do in showing the analysis of the measurement. Now, this case, we would like to highlight that it's only related to the connected reservoir case. So, if we have pressure inside the reservoir is equal to the surrounding pressure, and that could happen by having a continuous support from, for example, an aquifer beneath that portion of the free gas, and across the carborac we will have the same delta pressure, and this analysis could be only implemented in connected reservoirs. So that's a very important information to highlight. And now let me jump to the results right away. So results have been published in these two publications that have been conducted at the same conditions, the same using the same laboratory use and the same laboratory. So this is the contact angle measurement of our pressure over a different temperature that goes up to 343, and this is for hydrogen and CO2. Generally, you can see that we have we can observe two conditions that could be favorable for the gas storage. So as the pressure increases, the contact angle increases for both receding and advancing contact angle. This tells us that the contact angle are moving toward more, let's say, gas wet characteristic rather than the strong water compatibility that we desire. And if you notice, it has more higher impact on CO2 compared to hydrogen, and that's basically because of the low density of hydrogen compared to CO2. Now we added an analysis that's been frequently used, a semi-empirical correlation based on Young's equation, to calculate the equilibrium contact angle as a representation of the intrinsic contact angle to overcome the surface reference, which could be a drawback of using the tilted plate measurement, and which could limit the certainty of the measurement. But for us, it could give us the average of both, and that to just show you would show us basically the same trend. So pressure and temperature, they both have a great influence. And now let me shift to the capillary entry pressure that we've calculated, plotted against the pressure. So, and that's correlate with the contact angle. So as the capillary entry pressure drops with the pressure, that means we have less resistance to the buoyancy pressure exerted by the gas. It's more severe in the CO2, again because we have hydrogen has a very low density compared to CO2. Now we try to use a typical value for a mica portrait radius, which could go as high as 10 nanometers. And you can definitely identify the great impact into the hydrogen injection. So the lower is the portrait radius, definitely will have a lower capillary entry pressure, and that's what we showing from our analysis. And again, we follow the same concept by calculating the maximum height that we can have from a free gas, and also related to the portrait radius and the change in temperature and pressure. So now our favorable condition could be a warmer reservoir with very low pressure and very tight caprock with a very low portrait radius. So this is just the kind of conclusion using a pure mica. Now, what happened if we have the implication of having a high concentration of organic acid? So the experimental work selected the 4 representative acids and that we aged the pure mica with, and that's what we're trying to assess. So we pick the analysis, plot them with the an increment increase in the organic acid concentration, and that's what we're showing from these 2 plots. In the x-axis, you would see the organic acid concentration. It's a minus log of the concentration we used. So what we have here is 10 to the power minus 2 up to the 10 to the power minus 9. So as we increase the concentration going this way, we will definitely have a higher impact shown by the data that could go even above 90 degree of contact angle, and it's more severe in the CO2 case compared to hydrogen. Doing the same just to show an average trend using the equilibrium contact angle calculations, and this case is only for a specific pressure and temperature, that just to show you an example. So they have a high influence on the contact angle, and looking at it from the capillary entry pressure and maximum height of the gas column, we can see the highest the concentration we have from inside the mica sample, we will have a very low capillary entry pressure, which could go to a negative value, which could also create a negative suction of that gas, which allow the invasion of the gas throughout the caprock. And this is showing in terms of the maximum height in the gas column, which shows some negative values, means that we have that much of gas inside the sample. Now, the experimental work also extended to include the use of nanoparticles. In this case, since we have mica, and nanoparticles are a surface activating agent, the aluminum oxide was way so suitable to be used with mica, and that's what we used. So we picked only one concentration, the highest concentration that we have, and the objective here was to target identifying the optimum concentration of the nanoparticle that could be used in a real situation, that if we inject it back, will we be able to effectively restore the wearability. And that work being done and published in a recent publication, and that's what we're trying to show here. So the contact angle plotted with the concentration of the nanofluid, you can see that there is a certain concentration of the nanoparticle fluid where we have an optimum influence in the contact angle, and that's at 0.25. It's not 0.025, and this is what we're showing here, and that's basically the practice. It's only at the lab scale, but this, if we want to upscale, there's a lot of factor could get involved in this, but this shows you at the lab scale what can be done to prior going for a larger scale storage of CO2, for example. This is only CO2 data, so by that we would like also to show you some of the capillary entry pressure measurement, how we could look at it from a different point of view. So you can see the capillary entry pressure. We used the different portraits just to show also again the influence, but you can see the capillary entry pressure has been increased, and to an optimum value. Even if we go beyond that, we will not have that value or that concentration of the nanoparticle. Now, with that, I would like to conclude. So we showed that using a pure mica, the sealing efficiency could increase with decreasing pressure and increasing the temperature for both hydrogen and CO2. Smaller pore size is it's better for an efficient sealing. Higher the concentration of the organic acid, the lower is the efficiency, and also will have very low, let's say, maximum height of the stored gas. Finally, nanoparticles as a technique being used in the industry to restore or alter wettability has been exploited here, and it's showing that yes, we can also identify an optimum concentration that could help to restore the wettability into more favorable condition for gas storage. So these are the references we used, and finally, thank you for listening.